Good afternoon, everyone. Thank you so much for being here. Now, a couple of quick housekeeping things before I kick off. Firstly, I will be talking about a real rail accident, and so fair content warning to anyone with a slightly squeamish stomach for said topics. That said, the most serious injury we'll be discussing today is a dislocated knee. Hopefully that's amenable to everyone. This talk is based off the rail investigation report by the Australian Transport Safety Bureau, and I think it's important that I put this up on screen to ground us. Readers are advised that the ATSB investigates for the sole purpose of enhancing safety. Thankfully, I am not a representative of the ATSB, and so the emphasis, explanation and analysis, unless otherwise cited, is for the dramatic effect for this talk, and not the contribution of the original authors. Furthermore, and now perhaps slightly more obviously, we will be taking this report above and beyond its originally intended means so that we can learn some lessons in the software and technology space. Right, let's set the scene. It's shortly after 9 p.m. on Monday the 3rd of February 2003. It's warm, approximately 27 degrees, and there's a light northerly breeze. We're in Melbourne, and the scene before us is a busy Spencer Street station. For anyone familiar with Melbourne, Spencer Street was renamed to Southern Cross about 2 years after this accident. The country platforms, as they're known, are the terminus for most long-distance country trains, and all 7 platforms are full of locomotives and trailer cars for their various scheduled departures. And as such, there is no spare trackage or platforms. On platform 2 specifically is an N-class diesel-electric locomotive, N463, dubbed the City of Bendigo. It's about to depart and operate train number 8141, a service to Bacchus Marsh. It's ready to depart with 4 trailer cars attached and will soon have a driver, a guard, and all its passengers on board. The signallers are preparing for imminent departures and have set the routes for 4 trains, specifically the overland service to Adelaide on platform 1 and our Bacchus Marsh service on platform 2. We got all this memorised? Great. We'll be back to this scene in a few minutes. Almost 17 kilometres away, to the north of Melbourne, is a 3-car EMU, or electric multiple unit. This EMU consists of motor car 393M, trailer car 1048T, and motor car 394M. In this image, we've actually got 2 3-car sets combined to make a 6-car set, and you can see that it's being hauled off the electrified network, and you can see the pantographs are in the down position. You see, these trains are designed to be able to run in both directions, allowing the efficient turnaround at terminating stations. As such, the train can be driven from either end, as there are drivers' cabs at opposite ends. With 393M leading the way, train number 5859 gently arrives as scheduled into Broadmeadows station. The weather is similar, with a noticeable breeze gusting at about 20 kilometres an hour. Blowing towards the city is emphasised here. I think that might be important. We're early in the privatisation era of Melbourne's train network, and we're in M-train territory. Broadmeadows is, at the time of this incident, the last station on the electrified network, and as such, it's the terminating station for passenger services operated by M-train. If you're a Melbourne local, you'll probably know that this line has since been extended and is now called the Craigieburn line. The driver noticed that the passenger information display on the platform was showing the next train as being a Seymour service. This led him to think that he may have to perform a shunting movement to clear the platform after arrival. With this assumption, the driver isolated the controls and applied the brake, and then had to wait for quite some time. Eventually, he exited the leading cab. We assume he intended to speak to the signaller to confirm this shunting manoeuvre, since the signal box is on the platform at Broadmeadows. Thankfully though, by the time he had stepped onto the platform, the displays were showing the next service to the city, so there'd be no need for that assumed shunting. It's now time for our train to become 5264, so the driver briefly re-entered the cab and entered this number into the controls. This required briefly cutting in the leading cab once more. With the information displays set, The driver cut out the cabin for a second and final time and proceeded to change ends. Changing ends is a formal procedure, documented in 3 different documents. En route to cab 394M at the back of the train, our driver deviates to the bathrooms. Now friends, I apparently have been promising people to do a near real-time recount of a runaway train, and so perhaps now is the time that we should keep an eye on the time and speed of our train. By entering the train number 5264 into the controls, the driver was using a system known as POTS, or Position of Train System. The train can retrieve information from a server and use that to set the onboard passenger displays. POTS manages more than just passenger displays, however. It can track crude telemetry as well, such as the pantograph position, up or down, the train speed, and importantly, whether or not the brake valve is open or closed. The speed of the train in this talk is calculated primarily using this POTS data, as well as some explicit speculation from the investigators around its peak speeds. Now, at some point while I've been explaining POTS to you, train 5264 has started moving ever so slightly up and out of the station, in the direction of the soon-to-be intended movement. Movement will have been extremely subtle at first, as the train took almost 2 whole minutes to reach the end of the platform. We don't specifically know why the train ran away. Broadmeadows is on a 1 in 5,000 gradient, so to the naked eye it's completely level, but the report speculates that the northerly breeze may have contributed to that movement. And so, assisted by gravity and a little bit of wind, our train passed the up signals at the end of the platform, and POTS recorded our first speed measurement of 3 kilometres per hour. Shortly thereafter, a passenger complained to the station manager that their train had departed early. The station manager, confused by this, proceeded out to the platform to see 5264 in the distance. They then conferred with the signaller, who was also unsure why the driver had departed early. It's now almost 3 minutes since the initial movement of our train. And would you know it, our driver reappears. As one would, the driver spotted the train rolling away and took chase, jumping onto the tracks and sprinting after car 393M. An average 30 to 40-year-old can run about 4 to 5 kilometres per hour, but despite our driver's best efforts, he was unable to chase down the train. As 393M got smaller and smaller into the distance, the driver stopped chase and used a phone at the signal box in order to convey the news back at Broady. It's at this point, about 5 minutes after the train's first movement, that Metrol was alerted to the fact that they now had a runaway on their hands. Metrol is the operator of the Melbourne Suburban Rail Network, and they're responsible for train movement and signalling. POTS isn't specifically a real-time monitoring system. The only way to track our train is to observe it using CCTV on the platforms. Now, to complicate things further, and as a room full of engineers, you can always complicate it further, CCTV isn't centralised to Metrol, which means that we had to rely on station staff to check as the train progressed through their station. The safety report highlights this as a contributing factor that influenced the decision-making over the next 10 minutes. Nobody quite knew where the train was or how fast it was going. Now, speaking of our train, let's see what line is ahead. Our runaway has recently departed Broadmeadows, and that there is a big hill. At its peak, the Glenroy Bank is a stretch of 2.8 kilometres of 1 in 50 incline. With gravity assisting, 5264 has nothing to stop it, well, other than a small hill towards Essendon, and then it's all the way downhill to Spencer Street. As our train races through the night, we might start to ask ourselves what systems would normally stop a train. Let's talk about fail-safes in engineering. It's important we have a consistent understanding to ground this conversation. A fail-safe is a mechanism that is designed in a way that, when failing, defaults to a safe outcome. That's not to be confused with fail secure or fail open. We'll touch on those a little bit later. Let's see how this design thinking applies to the brakes on our ComEng EMU. How might they stop the train? The train is fitted with a hierarchical system which provides a primary braking mode, with additional backups. The brakes are controlled using a handle applied by the driver's left hand. Ultimately, during a braking failure, each subsequent subsystem cuts in at a similar level of braking effort determined by the position of that handle. Ultimately, during a braking failure, each subsequent subsystem should result in an emergency application. This is a really important design decision. If multiple brakes fail, they are designed to apply the emergency brake and ultimately stop the train. If a train is not moving, it is deemed safer than a train that is moving that didn't want to be. Now, in this particular train, the primary rheostatic brakes were noted as being faulty by the previous driver. And that meant we were using the electro-pneumatic brakes, or EP braking. EP brakes convert the electrical signals from that brake handle into air pressure in the braking system. Now, the ATSB report explicitly excludes the rheostatic braking failure as a contributing factor for this incident. And it has further extensive coverage into the function and operating procedure of the brakes in question. The investigation also looked at the practices that drivers used when completing the changing of ends procedure. We saw that back at Broady. Of note, it found that several drivers had different practices when it came to the specific sequence of steps in applying the brake and cutting out the cab. The report also notes that it was quite common practice for drivers not to apply the park brake when just changing ends, and that was the case for 5264. Now, you'll recall I said POTS measures whether or not the brake valve is open or closed. Well, thanks to this data, we know that the brakes were at least initially applied correctly as per procedure. Ultimately, though, we have a runaway train on our hands, and so those brakes definitely released. Now, remember I said the ComEng EMU is designed to be controlled from either end, using its two driving cabins, but importantly, never both. As such, the brakes must be cut in at the driving cab, and it's a valid configuration to have no active cab. So, since our driver never made it to 394M, our train is racing through the night with no active brakes, and no active headlights either. Now, another failsafe, perhaps better known to many folks here, is the driver's pilot valve, or sometimes known as the dead man's handle. This brake lever must be held in an actively open position, and this relieves brake pressure. It then defaults to a closed or brake position using air pressure in the brakes. And yet, once more, this failsafe is only enabled in an active cab and was not active in our runaway train. The third and final failsafe to discuss is the automatic mechanical trip arms, known as train stops. These are fitted to all ComEng trains, and it's quite a delightfully simple system by design. When signals are set to stop, a small arm is raised next to the track. The train stop is a lever lowered beside the train. If it passes a signal at stop, it triggers the brakes. Now, until this point, the train had been proceeding through green signals since the Broady signaller had set the route minutes earlier. But our failsafe was not to be. This because the train stop is only enabled in an active driver's cab. Has anybody here noticed a trend? A lot of our fail-safes are dependent on the train having an active cab. Ultimately, the report highlights that the adherence to procedure plus applying the park brake as the only combination of systems to prevent a runaway train when changing ends. Now, as such, our runaway train can proceed at full momentum through its first stop signals at Glenroy Station. In railway terms, up is the direction of travel towards a major location. At Glenroy, the station is then followed closely by the first level crossing in that up direction. In this configuration, trains that are scheduled to stop at Glenroy will trigger the level crossing slightly later, and this helps to reduce dwell times and optimise for road traffic flow. Well, with gravity as our train driver, 5264 did not slow on approach to Glenroy. It proceeded through the stop signal at speed. Thankfully, the automatic boom gates had lowered automatically, but with little or no safety margin. The other level crossings on our route were operated similarly, or manually set by signallers who had the forethought to close them early. You might have realised by now, nobody quite knew what to do with the runaway. I suspect everyone had an element of decision paralysis. It was unclear if any passengers had boarded the train back at Broady. They certainly might have. The train doors had been left open, and our driver had intentionally set the passenger displays. It is 2003, so we're not expecting many people to have a mobile phone to call for help, yet alone post TikToks of their experience. The lines ahead of Metrol presented relatively few options to the signallers. To stop a train with gravity, you'd have to route the train first through Flinders Street Station and then up hills toward the east. Not only would you have to navigate the tight curves of the viaduct, but you'd then be traversing busy passenger platforms in the heart of the city, where the trackage is designed for very slow speeds. They'd also have to hand over to Connex for several of these routing options. Connex is another rail operator in Melbourne. You'll remember I said this was the privatisation era. They also couldn't physically route the train through the city loop, since there were trains already in there. The signals have a blocking mechanism that prevent trains from entering the tunnel when it's already occupied. You also don't want to risk a derailment in a tunnel. There are some sidings and yards around North Melbourne. However, these also have very similar tight curves and some flyovers, and they were deemed equally likely to cause a derailment with possible passengers on board. Eventually, they made the only decision that they really could, to route it towards the country platforms at Spencer Street. So, Metrol called Spencer Street Station's number 1 box with less than 7 minutes on the clock. And that conversation went like this. Yeah? Yeah, who's this then? Yeah? Yeah, mate, we got a situation here. We got the runaway train, the up train from Broady. Yeah? It's already at Glenbervie going towards Essendon. Just wondering, they suggest we're going to bring it towards you. You're going to bring it towards me. Yeah, number 1 box. Oh, really? And where am I going to put it? Anywhere that's safe for a train to stop. If that one, we'll send that towards Spencer Street. I haven't got a platform to put it in. Oh, you got no platform to put it in? Nope. The only place I'll have is platform 1 when the Adelaide goes, but then it'll run down and hit the bottom anyway. Yeah, that's the thing. And then it'll run out of wire, and then of course nothing moves. And that's what they want to do. Yeah, that's right. Righto. Okay. No worries. See ya. Hey, listen. Needless to say, this conversation didn't really convey the seriousness of what was happening. I get the feeling number 1 box just assumed they'd use platform 1 after the Adelaide departs in 10 minutes. Now, while all of this had been going on, Metrol had decided to isolate power to the line. This report doesn't specifically say why they thought this would stop the train, but staff at the time didn't have the completeness of hindsight that we have, and so we can't throw too many stones. Perhaps they legitimately thought the train was under power. This decision, however, did affect POTS. We can see from this table of data that once the power was cut, the runaway train was recorded in 0000, and this is a manufacturer default after a power outage. These measurements are therefore assumed, but congruent with our timeline of the runaway. Ahead of our runaway, the previous Broadmeadows to Flinders Street service had just left Kensington, operating as 5262. A decision was made to get it out of the way via the main suburban lines at North Melbourne, and this had to change the existing routes. Once a route is cancelled, new points cannot be set for 90 seconds. This timeout prevents the points from changing while a train is progressing through the signal. The driver of 5262 was not expecting this delay and was about to exit the cab and call for information using the signal box phone. The report notes that he was surprised by his radio actually working, and he was informed by Metrol about a runaway. Approximately 2 kilometres behind him, the Kensington signaller observed 5264 was, quote, going like a tyrant. And sure enough, 5262's driver saw the runaway approaching behind him. With some quite understandable enthusiasm, 5262 sped through the now green signal and onto the main suburban line at 62 kilometres per hour, well in excess of the 40-kilometre limit. The interlocking of these points would not revert until 5262 had vacated that circuit. For a fleeting second, and with static on 5262's radio, the Metrol signaler's display showed the trains had actually collided. Data later shows us that it was a dead heat, and that the points had changed within a second of 5264 speeding through. With hindsight, we can see that the routing decision did contribute to the near miss. However, the ATSB report does not lay fault with this decision. It describes the runaway train as uncontrolled and uncontrollable. Furthermore, it emphasises that the only options available to Metrol officers were confined to these contingency measures, only rerouting trains and informing personnel. The report highlights that the emergency response plan did not deal with runaway trains either. Ultimately, nobody had grasped the actual speed of our runaway, and they made the best decision they could with the available time. Hang on. Distracted by our near miss at North Melbourne, Metrol still hadn't been in touch with Spencer Street about the situation. We don't have a complete transcript, but we can determine that the situation was very well understood now. 5264 was routed towards Spencer Street via the East Country line, and reports note that the signallers continued to complain they didn't have a clear road. Spencer Street country platforms had locomotives and trailer cars on all 7 platforms. The signallers made a last-ditch effort to take the route off the Bacchus Marsh train on platform 2, but the points were still on timeout. 5264 sped through the last available points and claimed the route previously set for 8141. As 5264 sped towards the platform, there was nothing more that could be done. And at 9:33, 5264 crashed into 8141 at 75 kilometres per hour. The driver of 8141 had no advanced warning. It was only in the final seconds that he saw the cab of 394M hurtling towards him that his surprised shout was heard and he vacated the cab. At the time, 8 passengers reported minor injuries, with 4 requiring brief hospitalisation. The most serious injury was a dislocated knee, and all patients were discharged the following day. Shortly after, a police helicopter flew over the route of our runaway using a thermal imaging camera to determine if any unknown injuries had occurred. Thankfully, none were reported. Subsequent train drivers were instructed to proceed with caution, and Broadmeadows services resumed very shortly after. But it was still several hours until the full length of the line could be examined for track and infrastructure damage. Approximately 2 days after this incident, the rail safety regulator published the following bulletin with some clear and unambiguous guidance. All operators of ComEng and Hitachi rolling stock are to amend work procedures and instruct train drivers to use the park brake when changing ends of trains, for any reason. The investigation resulted in 30 individual findings and made 20 actionable recommendations. Of note, there were 6 contributing factors to our runaway. The duties associated with changing ends were contained in 3 different documents. The release of the brakes was a result of the manner in which the driver's controls were isolated. The park brake was then the only defence. The park brake was not applied. The runaway was neither controlled nor controllable. No options were devoid of risk, and every alternative examined presented either danger of collision or derailment. The flow of communication from Metrol to Spencer Street signallers was hindered by dealing with the near miss. And the incident duration, structure of visual information, and the voice communications contributed significantly to the lack of a more favourable outcome. And this is with respect to both the final position of 5264 and any warnings that could have been made to people at Spencer Street. Well, we've taken a look at several fail-safes in this system design. considering the failure modes of our software also leads us to consider things like fail secure or fail closed systems. 2FA is a great example of this. Irrespective of delivery rates, the failure mode for sending an OTP code is that it fails secure. You can't log into the system unless the system is working as intended. Sometimes the failure modes and the design goals can be in conflict with one another. And funnily enough, I'll just cite the Wikipedia article on this. It illustrates it with quite a poignant example. During a building fire, a fail-safe system might open all of the locked doors in the building in order to aid evacuation, but this fail-open design is also insecure by default. As technologists, it's incumbent upon us to consider the ramifications of design decisions, not just for the happy path of our business case, but also the consequences of failures along the way. The more complex the system becomes with subsystems and services and dependencies, the more difficult it is to evaluate all the possible outcomes. Modern day operating practices do teach us about testing in production, with large-scale observability allowing us to make rapid decisions about how we operate the software that we build. In the case of our runaway train, Metrol signallers had no real-time insights into the system they were operating. The closest they had was some visibility using the POTS transponders at certain signals. Even today, as we approach the turn of the quarter century, I encounter complex software systems that have little or no observability, and that means that their operators are flying blind. Just last week, I was brought into an incident where engineers had mistakenly failed open to meet a business case. This was causing infrequent but catastrophic user impact in the failure scenario. And this cascaded over several weeks until the appropriate telemetry could be instrumented in order to observe the complexity of the stack they were working with. The incident management of our runaway train spanned several operational and organisational boundaries. M-Train drivers, station staff, signallers, Metrol and Spencer Street staff. This doesn't even start to include all the mechanical engineers, the suppliers, the manufacturers of all of the various systems in use. It's not always possible to know the failure modes of every system we operate. Take, for example, just reaching for a third-party API, or, I don't know, an LLM that we didn't train ourselves. In these situations, some failure modes may be documented and communicated to their customers, but the operating parameters are almost always kept confidential, and every edge case cannot be enumerated. In these environments, it's incumbent upon us as software engineering professionals to carefully consider the outcomes of the business case and then architect our complex systems around this with fail-safes in mind, and ideally without some corresponding safety fails to match. I want to leave you today with the social permission to embrace your inner geek and go read a safety investigation report. Regulators around the world embrace their curiosity, and these blameless retrospectives make for fascinating observations. And they look at behaviour, communication, and technical design practices. Even 20 years on, we can still learn from their recommendations. Remember, always be observing and questioning your practices, and look at your processes, and keep an eye on improving safety in the systems that you build and operate. And always apply your park brakes.
Well, that was a runaway success.
Boom, boom. I'm very happy to take a question or two depending on the time, but we are right up against my little timer here with very few seconds to spare. So does anyone have a question they'd like to have a cube thrown at them for? Wonderful, on the left.
So as your countdown ticked down, you said the word crashed as it hit 0. How many times did you practice that out loud?
Let's just call that a large positive integer. There's clearly time for one more question if there is one. Was that a hand down the front? No? Going once, going twice. Sold to future questions in the corridor. Thank you so much for your time this afternoon. Have a great day.